Okay, so remember that controllability was preserved under similarity transformation. Namely, if we have two systems that are algebraically equivalent to one another, then if one of the systems is controllable, then and only then the other system is controllable. And since observability and controllability, we saw that they are dual concepts of one another. Therefore, it's not surprising that the observability is preserved also under similarity transformation. In other words, if you have an observable pair, okay, let's call it the matrices C and A, okay, C is your output matrix, A is your system matrix, then and only then the pair CT, T inverse AT, okay, where T is a matrix, it's of same size of A and it's inversible, so T's are coordinate change, so this pair is also observable. Okay, now one of those coordinate changes is such that it puts the system in a very nice form, in a very nice representation, given a given LTI system, and using that representation one can study nicely, or one can see clearly the unobservable dynamics and observable dynamics. Okay, remember that we did the same thing, or there was such a transformation, the dual transformation, from the controllability point of view, where for a given system we apply that transformation, special transformation, and then in the end we obtain a new representation, and in the new representation it was clear which subdynamics were controllable, which subdynamics were uncontrollable, and that representation, new representation, we call the controllable decomposition. Now we're going to introduce the dual representation, namely the observable decomposition. Okay, so this is the details about observable decomposition. Okay, so given an LTI system, okay, x that equals ax plus bu and y equals cx plus du, let's call this system 1. The order is n and output is a vector of size m and input is a vector of size k. And for this system, let n bar be the dimension of the unobservable subspace. Okay, be dimension of the unobservable subspace. Okay, and remember how we define observability through that dimension. If that dimension was 0, or if the unobservable subspace contained only the 0 vector, we called such system or such pair CA an observable system, an observable pair. But in general, that number or the dimension is 1 or larger, and in that case it becomes useful to put the system into a new representation. Okay, if you want to study observability. So that being the case, we can always find a coordinate change matrix, okay, T. And how we do that? Well, remember how we did that for the controllable decomposition. This T had two parts. The first part, the first set of columns, we labeled that matrix V, and the second submatrix, or the second set of columns, we called it we call that matrix U. Now, how V was picked for controllable decomposition was such that you look at the controllable subspace and then you pick a basis, an arbitrary basis for that subspace, and those basis vectors make the columns of the first submatrix of T, which we call V. And then U is just an arbitrary set of columns. And the only property that we require from U is that together with V, they span the entire space Rn, so that this transformation T is invertible. Now, for the observable decomposition, we do the dual thing in the following sense. We choose our transformation matrix T as in the following form, U and V. Okay, for controllable decomposition we had V and U. Now we have U and V, and V, okay, it's not difficult to guess. V now contains columns which make a basis for the unobservable subspace. Okay, so V therefore is size n by n bar. So it contains n bar linearly independent vectors in Rn, and those vectors span the unobservable subspace, where the columns of V span the unobservable subspace. Okay. Then, with such transformation, coordinate change matrix, we obtain the new dynamics, okay, in new coordinates, okay, which we call Z. That's our new state, and the transition from Z to the original state is through T inverse. Okay, so Z is T inverse times X. Okay, the system becomes okay. Now let's write the new representation, which we will call the observable decomposition. System becomes Z dot, okay, equals this matrix, which we will write in block form, times Z plus the new B matrix times U, and the output is the new C matrix times Z, our new coordinates or our new state, plus du. Now, let's partition this Z, the new coordinates, as the substate that corresponds to observable dynamics and substate that corresponds to unobservable dynamics. Okay, so Z sub O represents the observable dynamics, and Z sub U represents the unobservable dynamics. So together, this stacked subvectors, they make our vector Z. Okay. So we have ZO, ZU, ZO, ZU here. Now, after that transformation, the new A matrix, if you want, you can call it A tilde, has the following form. We have A0 here, 0 matrix here, A21, and AU. Okay, and this is BO, BU after the transformation. And here we have CO and 0 for the new C matrix. Okay. Now, this is such that clearly this whole matrix is n by n. It should be the same size of our original matrix A, and this A, the observable submatrix or the the matrix that corresponds to observable dynamics is n minus n bar by n minus n bar. It's a square matrix. Okay, n minus n bar by n minus n bar. N bar being the dimension of our unobservable subspace. Okay, and CO is m by n minus n bar. Okay, so that tells us that the size of the observable substate is n minus n bar, and the size of the unobservable substate equals the dimension of the unobservable subspace, which is n bar. Okay. Now, the relation between these new matrices and the original matrices, the original quadruple ABCD, are as follows. So, where the new A matrix A210 AU is in this form T inverse AT, and D is the same D. The new B matrix has this relation to the original or the old B matrix, and the new C matrix is related to the original C matrix through this relation, C times T. Okay. Now, why this ZU is, this dynamics are unobservable. Now, since observability has nothing to do with the input, for simplicity, let's figure out, let's ignore the input terms. Okay, let's forget about that. We have only Z that equals A tilde Z and Y equals C tilde Z. Okay. Now, this ZU cannot directly influence the output because this entry is 0. Okay, 0 times ZU. So ZU cannot directly appear in the output, or cannot directly influence the output, but it can, in general, okay, for general state space system, it can indirectly influence the output through the other state. But in this case, there is no such thing because ZU doesn't affect the observable subdynamics because this matrix is 0. So ZU cannot affect indirectly the output through the observable dynamics, or directly the output from the output matrix, since both these entries are 0. Therefore, we see nothing whatsoever regarding the behavior of ZU in our measurement, in our output. Okay, so that's why this is called the observable decomposition. And furthermore, and this is important, and the pair okay, COAO is an observable pair. Is observable, which justifies the that we call this subdynamics observable subdynamics. Okay. Okay. Now let's try to visualize this new representation on a block diagram, and once we do that, we're going to be able to say something about the transfer function. Okay, here is the block diagram representation corresponding to the observable decomposition. Now, we have two subdynamics, okay, which we call the observable dynamics and unobservable dynamics. Here we have, let's say, the observable dynamics, ZO dot equals AOZ plus the other effects, okay? In a sense, the input to that dynamics, V. Okay, so what we have here is ZO dot equals AOZO. Okay, we have no influence directly from the unobservable dynamics because this entry is 0, but we can have some effect coming from the input, okay, through this possibly non-zero BO term. Okay, so but let's now leave V as V. So that's the external input to the ZO dynamics. And we have the unobservable dynamics also. Let me put it here. ZU dot equals AU ZU plus, okay, plus W. Now, in this case, the W represents the external dynamics to the external input to the, or external force to the unobservable dynamics, ZU dynamics. Okay, now we're going to combine all those dynamics and obtain the output. Okay, and then once we have the output and once we have the input, we can see the path clearly from input to output, and by following that path we will be able to say something about the transfer function of the observable decomposition. Okay, one thing that we have to keep in mind is because this representation, observable decomposition, is algebraically equivalent to the original dynamics, original representation, they have the same transfer function. Okay, so whatever conclusion we reach regarding the transfer function of this decomposition, observable decomposition, it must hold true for the original system. Okay, so what's V? V is, okay, the external input, the observable dynamics. V is, there's only one thing that's affecting ZO dot, and that's BO times U, okay, other than its self-influence through A0. Therefore, if we have here input, then that input going through the gain block BO produces BO times U, and BO times U in this case is what V is. Okay, whereas for W we have the effect due to ZO through A21 and also the effect due to the input through this term BU. So we have to sum those two effects to obtain the total external influence on the unobservable dynamics. Okay, so here we have the gain block from the input, which we're calling BU. Okay, so the input is entering here, and that produces the BU times U term, and also we have the influence of the observable dynamics affecting ZU dynamics through this entry A21. So what we have is, so the outputs of these matrices are ZO and ZU. Okay, so what we do is we take ZO here, put the gain block here, which is A21, and that affects the ZU dynamics. Okay, now how about the output? So those are the dynamics for observable piece and the unobservable piece. Now let's construct the output. Okay, now output does not directly depend on ZU because this entry is 0. So output is CO times ZO plus DU. Okay, so we take from here ZO, pass it through the gain block CO, okay, and then we take here from here the input, pass it through the gain block D, add to this summer, okay, and together those two signals make our output in observable decomposition, and that produces the output Y. And as for ZU, it doesn't reach in any way the output of the system. Okay, so therefore, as for the transfer function, which studies the relation between input and output, clearly ZU dynamics has no effect on the output Y. Okay, so that means if you just ignore the piece of this block diagram below the dashed line, you will that will make no difference on the relation from the input u to the output y. Okay. Therefore, the transfer function of the entire system must equal the transfer function of the simplified block diagram, where we ignore the unobservable dynamics. Okay. So let's put that down as a remark. The transfer function of system 1, that's our original system, equals the transfer function of the observable decomposition, and the transfer function of the observable decomposition equals the transfer function of its observable part. Therefore, transfer function of system 1 equals the transfer function of its observable part, or more precisely, the observable part in its observable decomposition, and that is part. And that transfer function is what? Now, this is the transfer function in original parameters, in original ABCD matrices, and we have just shown that that must equal the transfer function of the observable part, where we have the ABC matrices as AO, BO, CO, and D matrix is the same as D matrix here. Therefore, that must equal CO SI minus AO inverse BO plus D. Okay. Now that we obtain the dual result for or from the controllable decomposition, namely the transfer function of the original system was equal to the transfer function of its controllable part. Now what we're gonna do is we're gonna combine, or we'll try to study the whole picture, both under controllability and observability lights at the same time, and that will give us the so-called Kalman decomposition. Okay, but before introducing Kalman decomposition, let's quickly put side by side both controllable decomposition and the observable decomposition for a given system. Okay, now let's remember the controllable decomposition, where we had ZC bar, let's say, okay? So C bar would mean uncontrollable dynamics or uncontrollable subdynamics, okay? Z dot equals the new A matrix of the controllable decomposition, which has upper block triangular form. ZC bar plus the new B matrix, and the output was ZC bar plus DU. Okay, now the structure of the A matrix was such that it was AC, A12, 0, AC bar. Let's call that matrix. Okay. And then the controllable decomposition makes no special claims on the observability. Therefore, the C matrix after the transformation was just an arbitrary C matrix with possibly non-zero submatrices CC and CC bar. C is for controllable, C bar is for uncontrollable. But the B matrix had a special form. It had something here and 0 for the uncontrollable part. Okay, and that's why in this form it's clear that you cannot affect through the input directly or indirectly the ZC bar dynamics. Okay, so what else the control decomposition told us? It told us that AC BC, this subpair AC BC must be controllable, and the transfer function of the original system equals the transfer function of its controllable part. In this case, we have CC SI minus AC inverse BC plus D. Okay, and then we had the observable decomposition. Okay, this is what we just obtained, where we had ZO bar. Now this is for observable, this is for unobservable. Okay, dot equals the new A matrix ZO bar plus the new B matrix U, Y equals the new C matrix ZO bar plus DU. Okay, the A matrix had the form A observable, this is 0, A21, AO bar, let's call it. This is BO, this is BO bar. The observable decomposition made no claims on the controllability properties of the system. Therefore, in general, the new B matrix was just an arbitrary matrix. But as for the C matrix, it had a special form which allowed us see the what is observable and what is unobservable for our new representation. So here we had CO and here we had 0. And the dual statement for controllable decomposition holds for the observable decomposition, where okay, we had the pair COAO is observable. Okay, and transfer function equals this thing here. That's just what we discovered. COSI minus AO inverse BO plus D. Okay, now the important thing about these decompositions is the presence of some zero submatrices, okay, in our representation. And due to those zero submatrices, we see certain things clearly. Now, let's obtain a very rough sketch of this representation and also that representation in a block diagram sense. So here we have controllable dynamics and uncontrollable dynamics. Okay, so suppose that this block represents the controllable dynamics and this block represents the uncontrollable dynamics. Okay, and then the controllable dynamics can be reached in a sense by the input U, because we have BC here, a non-zero term. So therefore here we have the input, let's call it, and that reaches this block ZC. Okay, so there's in a sense there's a path from U to ZC. That means, okay, or let's assume that means it's controllable. These dynamics are controllable. Okay, whereas for ZC bar, okay, ZC bar, the uncontrolled dynamics, note that you cannot directly reach through the input because this entry is 0. Okay, we cannot make an arrow and connect to ZC bar, and also we cannot take an arrow from ZC and enter that arrow to ZC bar because this entry is also 0. But ZC bar is free because we have possibly a non-zero entry here. ZC bar is free to affect the dynamics of ZC. Therefore, what we have here is this arrow only. Okay, so this very rough sketch, you can consider it as a graph. This is a node, this is a node, this is a node, and here we have some directed edges. We have an edge from input to ZC, so that would mean, okay, that ZC is controllable. we don't have a path, we don't have a connection from input to ZC bar, because the direction of this arrow is pointing from ZC bar to ZC. Therefore, these dynamics are uncontrollable. Okay. Since the controllable decomposition made no claims on the observability properties of the system. Okay, so we have possibly some influence of the controllable dynamics and also some influence of the uncontrollable dynamics that appear on the output. Okay, so this is a very rough sketch of this special block diagram. Now let's obtain the dual sketch in a sense. This time we have two blocks. Let's call them ZO and ZO bar. So this block represents the observable dynamics, the other block represents the unobservable dynamics. Since these dynamics are observable, they can be seen from Y. Okay, and then ZO bar, the unobservable dynamics, cannot be directly or indirectly, because we have 0 entries here, can be directly or indirectly read from the measurement, the output. Therefore, considering this as a node, there shouldn't be a path from this node to the output node. Therefore, the direction of this edge should be from ZO to ZO bar. Okay. Therefore, in this representation, where this is a node, and this is a node, you cannot reach from this node to the output. There is not a directed path from this node to the output node. Therefore, the dynamics represented by that node are the unobservable dynamics. Okay, it's a very simple sketch. And likewise, we don't worry about controllability in the observable decomposition. Therefore, the control will have some effect on both observable and unobservable dynamics according to this representation. Okay. Now, what we're going to do is we will try to combine these two pictures, okay, in a sense. And that will give us the so-called Kalman decomposition. Okay. Now, for controllable decomposition, we cared about what is controllable and what is not controllable. For observable decomposition, we cared about what's observable and what's not unobservable. Now, what we're going to do is we're going to care about everything. Okay, so that would produce 4 subdynamics. Okay, subdynamics that are both controllable and observable, controllable but unobservable, observable but uncontrollable, and the last subdynamics are neither controllable nor observable. Okay, so we will have, therefore, here we had 2 blocks, and now we're talking about 4 blocks or 4 nodes. Okay, so here we have 1 block, here we have another block, and our 4th block. Okay, and let's call this block ZCO bar. Let's call this block ZCO. This is ZCO bar bar, and this is ZC bar O. Okay. Controllable, unobservable, controllable and observable, uncontrollable, unobservable, uncontrollable but observable. Okay, and then, because we want this graph to represent what's controllable, what's unobservable, and all these things clearly, we have to figure out nicely the direction of the arrows. Okay, so let's again put here our output node in a sense. Okay, this is our output node, and let's place here our input node. U. Okay, and now the convention that we just invented is such that if you can reach from input by following a directed path to one of these nodes, then that node is controllable. Okay, and likewise from one of these nodes, if you can reach output by following a directed path, if there exists such a directed path, then that node must be that node must be observable. Okay, and if you cannot find such a path, then that node would be unobservable. So therefore we have to figure out all the possible edges, so that, for instance, from this we shouldn't be able to reach from input to this node, because this node is uncontrollable. Likewise, we shouldn't be able to reach from this node to the output, because this node is unobservable. Okay, and by doing that, we will figure out what edges can exist by removing all the edges that cannot exist. And then, looking at those edges, we will try to obtain the state space representation of this more intricate decomposition, where we simultaneously see what's observable and what's controllable, and also unobservable and uncontrollable. Okay, so we're going to figure out all these edges, and then we're going to place the state space representation. Okay, let's put it here. Okay, now this is our big state. Okay, Z dot, and that Z contains Z, CO, Z, C, okay, Z, CO, Z, CO. This is CO bar, C bar O, and C bar O bar. Okay, controllable and observable, controllable and unobservable, uncontrollable and observable, and uncontrollable and unobservable. This equals the A matrix of the Kalman decomposition times the state ZCO, 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 bar, 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 plus the B matrix times U, and then we have the output C matrix times CO, ZCO, 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 bar, 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 plus DU. Okay, and then this matrix will have 16 subblocks. Okay. And this B matrix will have 4 subblocks, and this C matrix will have likewise 4 subblocks. Okay, now we're going to figure out what subblocks should be 0 by looking at our graph. But first we have to obtain the graph. Okay, now this is observable, therefore it can reach the output. This is observable, so it should reach the output. So let's put those edges, okay, from observable nodes to the output. Now, as for controllability, this is controllable, therefore we should be able to reach from the input. This is controllable also, therefore we should be able to reach it from the input. Okay, and then let's put all possible, okay, now let's put all possible edges and then remove edges one by one by looking at what's controllable and what's unobservable and things like that. Okay, okay, so at first we put everything, every possibility, okay? And then what's not connected is here and here, okay? Now, so this, okay. Now this is unobservable, therefore it cannot reach the output node, okay? Right now it can reach output node, for instance, through this path, from here to here, and then from here to here, okay? Therefore, this cannot be part of our graph. We erase that, so that we, this cannot reach the output node. How else it can reach, okay, the output? Okay, so I put, this should be down. Okay, what else? This is also unobservable, okay? Since it's unobservable, it shouldn't be able to reach the output node, therefore we have to remove this edge, because if this edge is here, then from here we can move here, and from here we can move to the output, therefore we erase this also. Okay, that node is erased. How about controllability? This is uncontrollable, therefore we shouldn't be able to reach from the input node to this node, hence we erase this arrow, okay? And this is also uncontrollable. We shouldn't be able to reach from the input to this node, therefore we erase this arrow here, okay? Now this is again unobservable, therefore we shouldn't be able to reach this node here, because if you reach this node, then from this node we can reach the output, therefore this is not possible. And what else? This is uncontrollable, therefore we shouldn't be able to reach from input to this node. So as with this edge we can reach from input to this node by first reaching here, and then from here reaching there. Since this node is uncontrollable, this edge cannot exist here. Okay, and then what else? Okay, now this is input. Using this edge from input, first we can go here, and from here we can reach this node, but this node is uncontrollable, therefore we shouldn't be able to reach from the input. Hence, we also remove this edge. Okay? And what remains, okay, is all allowed. Now in this configuration, this is the most general case in which we cannot reach to uncontrollable nodes from the input node, and we cannot reach from unobservable nodes to the output node. Okay, so this is the most general graph that satisfies those two constraints simultaneously. And that graph, so let me put this edge here so that our graph looks nicer. And now, looking at this picture, we will try to figure out the entries of our A, B, and C matrices. Okay. So let's start with ZCO dynamics, that is dynamics that are both controllable and observable. First of all, every dynamic depends on itself, so the diagonal entries are here, A, 4, 4. Okay, so let's look at ZCO. ZCO is here, okay, so it's affected by the input. So we put here B1. It has a direct path from the input, so we have B1. What else? It has a direct path to output. Therefore, here we have something non-zero, possibly C1. And how about the other arrows? Now we look at these entries. Note that to ZCO we have an influence from the ZC bar O, okay? So there's an effect of this dynamics. ZC bar O is the third dynamics, okay? Therefore, here we have a 1, 3, possibly something non-zero. Other than that, we have no arrows entering ZCO, so that means these entries must be 0. Okay? Now, let's move on to the second dynamic, ZCO bar. Okay? Now, ZCO bar has an arrow from this node, has an arrow from this node, and has an arrow or edge from this node. So all the other dynamics are influencing this ZCO bar dynamics. Okay, therefore we have everything. A21, A23, and A24. Okay. Okay, it has a direct connection from the input, therefore here we have something non-zero, which we call B2. And then, as for the output, it has no connection to the output, no edge whatsoever to the output, therefore the corresponding block is 0 in the output matrix. For the ZC bar O dynamics, okay, note that there is no arrow whatsoever entering this node, therefore all these entries will be 0. And as for the output, it has a direct connection to the output, therefore here we have C3 possibly non-zero. And finally, for the last dynamics, both uncontrollable and unobservable, there's only one arrow entering it. It's from the ZC bar O, the third dynamics. Therefore, here we have A43. Okay, and the remaining entries must be 0. It doesn't have direct access from the inputs. That means this entry is 0. And finally, it does not have an access to the output node. Therefore, this entry is 0. And so what we've obtained is called the Kalman decomposition. Okay, so this whole thing is the Kalman decomposition, where all the observability and controllability properties are shown clearly. Now, of course, the important thing from the theoretical point of view is whether there exists a transformation such that, given an arbitrary system, through that coordinate change, we obtain this nice representation, which is called Kalman decomposition. Well, obviously there is, otherwise we wouldn't be calling it something. Okay, and here is the details about our elaborate construction, okay, which unifies controllability and observability properties of an LTI system. So this is the theorem on Kalman decomposition. For each system, x that equals ax plus bu, y equals cx plus du, there is a coordinate change z equals t inverse x, that yields the Kalman decomposition, the form KD. Okay, this is what we're calling KD, what we have obtained, for which the submatrices that appear here satisfy the following properties. Okay, the pair B1, B2, A11, 0, A21, A22. This pair is controllable. Okay, which we extract from the controllable dynamics. Okay, here. And then, as for observability, the pair C1, C3, A11, A13, 0, A33 is observable. Okay. And if you look at this first claim, if this pair if this pair is controllable, then the subpair A11, B11 must also be controllable, because the only way you affect this Z11 dynamics is through B1, because this entry is 0. Okay, and since the whole thing is controllable, its substates must also be controllable, subdynamics must also be controllable, and since this entry is 0, there's only way that we can affect these dynamics through B1. Therefore, this subpair A11, B1 must also be controllable. Through a dual argument, we can figure out that if this pair is observable, then the subpair C1, A11 must also be observable. And then combining those two observations yields the following: the triple C1, A11 and B1 is both observable and controllable. Okay, so the triple being both observable and controllable means that this pair is observable, and here this pair is controllable. Okay, and finally, now using controllable decomposition, we saw that the transfer function of a system equals the transfer function of its controllable part. We also saw that the transfer function of a system equals the transfer function of its observable part. And then when those two results are combined, the transfer function of the system must equal the transfer function of its both observable and controllable parts. Okay, the transfer function of the original system equals the transfer function of the both controllable and observable part. Okay. In other words, CSI minus A inverse B plus D. So that's the transfer function of the original system. That must equal the transfer function of possibly much smaller system, okay, given by that triple, well, and plus the D matrix. So that should equal CSI minus A inverse B plus D, where we have 1, 1, and here we have 1, 1 for A. Okay, so this transfer function equals the transfer function of the observable part. That equals the transfer function of the controllable part, and that equals the transfer function of the original system. Okay, now the A matrix is possibly larger than the matrices here, and these matrices are possibly larger than A11. Well, clearly they're larger than A11 in this representation. So that means that if it is the case, if they're actually larger, then it would correspond to the fact that certain poles and zeros are being cancelled. Okay, so from let's say an nth order system, we obtain a transfer function whose order is much smaller. Okay, so that's the relation, the indirect relation between unobservability or uncontrollability or both, and the pole zero cancellations while you're computing the transfer function.